This is the Theory and Calculations Lab lecture for the preparation and analysis of aspirin. Good news about this being a lab that goes along with organic chemistry is in organic chemistry, there's not a whole lot of math that goes on. A little bit of mole ratio and molar mass, some RF calculations, and we're done. So for this lab, the balanced chemical equation is given in the introduction between acetic anhydride and salicylic acid to make aspirin, which is called acetyl salicylic acid, and acetic acid. So acetic acid for us is just a product, but we don't really care about it. So for this lab, salicylic acid is our limiting reactant. And the thing we care about is aspirin. That's the product, the special product. He's going to get a star. Okay. It also makes acetic acid, but for this lab, what we're really interested in is the aspirin. So in the lab, right under the balanced chemical equation, the molar masses are given because these, you will notice, are a lot of carbons, hydrogens, and oxygens. So I'm just going to write them down here. So we've got them. So the molar masses have already been calculated for you. Okay, so flipping ahead to the lab. Number one, you are going to record the mass of salicylic acid from the lab. And then number two says moles of salicylic acid. So you're just going to use the molar mass right here. And the idea that 1 mole of, I'm going to write SA for salicylic acid, is equal to 138.12 grams of SA. You're just using the molar mass to convert grams into moles. I'm not going to demonstrate this because it's the end of Gen Chem 2 and I'm hoping you can handle molar mass on your own. Number 3 says the theoretical moles of aspirin. Well, to do that, we need to look at the mole ratio between these chemicals. And when we look at the balanced chemical equation, conveniently, it's a 1 to 1 to 1 to 1 mole ratio between every chemical. So once you've calculated the moles of salicylic acid, you can convert that to moles of aspirin, knowing 1 mole of salicylic acid is equal to 1 mole of aspirin. So you do have to show your calculation, but you should not really need your calculator to do the number 2 to number 3 switch. Number 4 is the theoretical mass of aspirin. So number 3 is the theoretical moles of aspirin. That's what you'll be using to calculate the theoretical mass of aspirin. Just be careful when you go from moles to grams to remember which chemical you're looking at. For number 4, we're looking at aspirin. So you're going to use the molar mass for aspirin. So your mass of salicylic acid and your theoretical mass of aspirin should not be the same number. They have different molar masses. So that's the calculations for numbers 2, 3, and 4. Number 5 and 6 are data values. For number 7, it says the mass of the dry product using the last weight. So what you're going to be doing is taking either, in number 6, the mass of the watch glass and dry product second weight, or mass of watch glass and dry product of third weight, whichever is the last number you wrote down. And take that value and subtract off the watch glass. And then the difference between them is going to be your mass of your dry product. Okay, that product, we're calling it product because we don't have any proof that it is aspirin, but we're crossing our fingers and hoping that it's aspirin. So when we do our percent yield, we're going to be comparing your mass of your product, which again we're assuming is aspirin, divided by the theoretical mass of aspirin. So the theoretical mass of aspirin, theoretical masses are the calculated maximum amount you could get if everything went perfectly. Okay, mass of product is what you really got. So you're calculating the percent yield. 100% would be glorious for this. That means you got exactly what you expected. So for this lab, for the percent yield, you're going to get whatever you get. And at the end of the day, as long as you're above 25%, you're fine in terms of your accuracy. These organic reactions are not, even if you did everything perfect, there's so many little places for something to go wrong. So you're just going to do the math, okay? You do have to go to the correct number of significant figures for this. And then there are no calculations for the phenol test, but for the thin layer chromatography, there are calculations. So with the thin layer chromatography, once again, you'll have your TLC plate with spots. You'll have your salicylic acid, your aspirin, and your product. I don't know what they're going to look like. yours will look like whatever they are. You have to measure the distance between the bottom and the middle of the spot. Oh, sorry. For each of the spots and record that. Now it needs to be measured in millimeters. You also have to measure the distance, between the bottom and the top. That's the solvent distance. So you can eyeball this usually to determine what you think was in your product, if it more closely resembles salicylic acid or aspirin, or if it has both. But we need some evidence more than just your eyeballs. So that's what the RF values are for. RF values are decimals comparing the distance the spot moved compared to the solvent. And if we see two spots that look visibly like they're the same, so like to me, this one and this one look very similar to each other, their RF values will be similar. And so that's our evidence that that is the case. So you're calculating the RF value for pure salicylic acid, which should only have one spot, pure aspirin, which should only have one spot, and your product, which could have one or two or three spots. And I don't know what it's going to have. It really depends on what you made. Okay. You have to calculate the RF value for each spot you get. Do go to decimals. Don't make this a fraction. Okay. You need to actually do the decimals and get the correct number of sig figs. And then you have to show the calculation. Then based on those RF values and what you saw and the spots that you saw, you'll answer the questions below that. Math-wise, that kind of takes care of the math. Like I said, there's not a ton of math. On the post-lab questions for number 4, just a reminder that Le Chatelier principle is something we talked about back in chapter 15 and 16 and 17 with equilibrium. So when you're answering that question, if you need to go back and check it out, do that. You're going to be referring to the balanced chemical equation in the introduction of the lab, and then using the Le Chatelier principle about is it shifting left or shifting right, making more reactants, making more products. And then number 7 and number 8 are both calculation questions. But for number 7, it's a very similar type of problem to what we did in this lab between the salicylic acid and the aspirin, only this time it's between the phenol and phenyl acetate. So their molar masses are not given, but you will need them. So that's a thing that you can calculate. And then on number 8, again, it's similar, but the difference is number 8 is a limiting reactant calculation. All right, that came back from Gen Chem 1 because they're not telling you which one's a limiting reactant. So like in our lab, salicylic acid was a limiting reactant. So acetic anhydride we ignored. Yeah, we added it because we had to, but we didn't do any calculations with it because we added way more than we actually needed. But for number 8, you're going to have to take into account both chemicals. So in other words, you're going to have to calculate the mass of the cyclohexyl acetate, starting with the 2.75 grams of cyclohexanol, and then repeat that calculation to calculate grams of cyclohexyl acetate, starting with 4.00 milliliters of acetic anhydride. The density of acetic anhydride is given because you'll need to convert those milliliters into grams, so you can do a mass stoichiometry problem. So check back out limiting reactant problems. It's going to be molar mass and mole ratio are the unit factors that we are using for this, though. So let me know if you have questions.